Alrighty, PreCalc, we are done with chapter 11, so obviously we are now moving on to chapter 13. Okay, so sequences and series. A sequence is simply a list of numbers. We've kind of done sequences and series before in Algebra 2, so we're just going to kind of refresh our memory on this stuff. Maybe introduce some things that are new. I'm not sure how many of you have dealt with the sigma notation for sequences, so we're going to make sure we cover that. But for the most part, 13.1 here and 13.2 should probably be review. So we'll just kind of go through this stuff. So again, sequence is just a list of numbers. That's all it really is. And we see an example there, right, for election years, I guess, right? The notation for sequences, remember that we use subscripts. So we have like a sub 1 represents the first term in the sequence, the first number in the sequence, a sub 2, the second term, so on. And then we can say a sub n for any specific term in the sequence, right? So if we want to find, for example, the 43rd term in a sequence, then n would be 43. Make sense? All right. So here's the real stuff we want to know. How do we write these sequences? So this is the formula for an arithmetic sequence. So we are in 13.1, and it's not even writing at all here. That's cool. Good job. 13.1, sequences. And the first type of sequence we're going to talk about is an arithmetic sequence. Arithmetic sequences. So an arithmetic sequence is a sequence that either increases or decreases by a constant rate every time. Sounds familiar? So a list of numbers that increase by a constant value. So I just said increase because now we can just kind of say that the constant value can be negative too, right? So we know that it can also decrease. It's essentially a rate of change, right? It's essentially a linear function. And so here is the formula for finding a specific term. To find a specific term, we're going to use a sub n equals a sub 1 plus n minus 1 times d. So what do these things represent? That's the first term. This is the term we're looking for, the term number that we're looking for, I guess. Sure, we'll go with that. And this is our constant rate of change. Simple enough, right? So, for example, let's see what the book has. Write a formula for the general term of the odometer sequence of the car that has driven 8,000 miles per year and has gone 15,000 miles when it was bought. What's the car's odometer reading 7 years after its purchase? Okay. So this is, was that on screen? If that wasn't on screen, there it is, over there. Okay, so example 5 from the book. 8,000 miles per year, it's gone 15,000 miles when it was already bought, so 7 years after. Okay, cool. So what we're going to do is we know that the first term, right, the starting value in this sequence would be 15,000. And we know the constant rate of change here would be 8,000 per year. And so the sequence, a sub n, equals 15,000 plus, let's keep it general first because that's what we want, n minus 1 times 8,000. Okay? And if we want to know 7 years later, we are looking for a sub 7. That's a 7. A sub 7. And so we're doing 15,000 plus 7 minus 1 times 8,000, right? Or essentially just 6 times 8,000. So a sub 7 equals, what's 6 times 8,000? 48, right? And what's 48,000 plus 15,000? 63,000? Right? Yes. Okay. Awesome. Ah, okay. So the book, interesting. So what's the car's reading 7 years after its purchase? So technically speaking, 7 years from the date of purchase is the start of the 8th year. So n equals 8. Okay, they threw me a little curveball there. So instead of finding a sub 7, we would be finding a sub 8. And there's that work there. My bad. That was a little curveball there. All right. Okay. What's the connection between an arithmetic sequence and a linear function? Essentially, an arithmetic sequence is basically like a discrete linear function. What I mean by that is, let's take this function here. So let's take this linear function, y equals 2 plus x minus 1 times 5. Okay? That's a linear function. It's just written a little differently, right? Okay, and then let's take this sequence, a sub n equals 2 plus n minus 1 times 5. What's similar and what's different about these two things? Well, what I mean by when I say that a sequence is basically a linear function, but it's like a discrete linear function, is that in this y equals linear function, okay, I can plug any x value in and I can output any y value, right? I could plug in fractions, I could plug in decimals, I could plug in irrational numbers, I could plug in anything, right? The domain and range of a linear function is all real numbers. So what we get is something that looks like, let me just do that over. What we get is something that looks like this. It would be starting at, technically speaking, be starting in the negatives, -3, right? If I solve this out for the y-intercept. And it would be a nice, smooth, continuous line going up by 5. Right? Okay. With this sequence, what do I get? Well, with the sequence, you can't plug in fractions. You can't find the 4.5 term, right? That doesn't make any sense. So with the sequence, essentially, we're just starting at our 2 and as the first term, when n equals 1, and we're going up by 5 every time, and we kind of get something like this. Right, so that's the difference between these two things. Not much difference in the pattern itself, right? It's adding 5 every time. The difference is that the linear function is smooth and continuous. There's values in between every single other value. And here it's kind of discrete. It's just certain steps, certain values. Okay? So that's arithmetic sequences. So now let's move on to geometric sequences. A geometric sequence is a sequence that, again, is a list of numbers that increases or decreases, remember, so that increases by a single multiplier. So instead of adding or subtracting a certain number, we're going to be multiplying by a certain number. So let's take a look at this example. You were offered a job at a salary of $40,000 for the first year with a 5% pay raise every single year. Under this plan, your annual salaries form a sequence with terms. So the first term, 40,000, that's the amount you make. The multiplier here, since we're increasing by 5%, we're multiplying by 1.05. Now we're making 42,000. Now we take that 42,000, multiply by 1.05 again, or we can essentially think of that as just repeated multiplication, right? And so the exponent, we can start using exponents, increases, and by the fourth year, we're making 46,305, and so on, okay? And so based on this sort of pattern, if you notice, a sub 3, we're using an exponent of 2, a sub 4, we're using an exponent of 3, we can kind of figure out what this standard form will be, and that will be, again, to find a specific term, we're going to use a sub n equals a sub 1 times r to the n minus 1. Again, that is not seen. There we go. Again, this is the first term. The r here is our multiplier. And the n is the term number that we're interested in. So let's take a look at example 7. Write a formula for the general term of the salary sequence that starts at 40,000 and increases by 5% per year. Oh, okay. And what's your salary after 10 years on the job? All right, let's see. So what's a sub 1? 40,000. Our r, 1.05. And so the general form is a sub n equals 40,000 times 1.05 to the n minus 1. Okay, so here's why I messed up last time. Because the first term is essentially considered the 0th year, which is kind of strange. So if I'm looking for the 10th year, I'm actually looking for the 11th term. It's kind of strange there, but it works. So we're looking for a sub 11. So 40,000 times 1.05 raised to the 11 minus 1, or raised to the 10. I'm not going to do that in my head because that would be weird. Not weird, but impressive, I guess. 40,000 times 1.05 raised to the 10, and it looks like 65,000. So we got 65 $1,155.79. Assuming since it's a salary, they're going to round it up. And okay, yeah, the book rounded to the nearest dollar. Did they tell me to do that? They didn't. Okay. The book would be more generous to you. I would, if I were your employer, I would not be rounding that up. So, connection between geometric sequences and exponential functions. Very similar to arithmetic sequences and linear functions, right? An exponential function is smooth and continuous. It's that individual line, right? If I do something like y equals 2 times 5 to the x minus 1 versus a sub n equals 2 times 5 to the n minus 1. Again, this one's going to look like that, smooth and continuous. This one's going to look like this, kind of discrete steps. Okay, that's it for 13.1. So I will see you guys later.